Imagine writing, I don't know, thousands of lines of perfectly functional code, right? You deploy it, and then you just watch your program completely drag.
Oh, it is the worst feeling.
Yeah, and you profile it, assuming you have like a rogue infinite loop or maybe some poorly optimized recursive function somewhere.
Right, because that's the obvious culprit.
Exactly. But your logic is actually sound. You eventually realize that the bottleneck isn't the algorithm at all. The program is dragging because the very shape of your data is actively fighting the compiler.
It's a profound realization for any developer, honestly. You discover that you haven't just been using an inefficient function. You've actually built your entire architecture on a fundamentally flawed model of reality.
Yeah.
The data structure itself is the bottleneck, and that is really where the true engineering has to begin.
Welcome to the deep dive. Today our mission is to explore, well, the architecture of efficiency. We're looking at how we structure information, specifically by going behind the scenes of a pretty fascinating software evolution.
It's a great case study.
It really is. Set the stage for you. We're pulling from a highly technical developer blog post. It's titled, Notes on Haskell Programming Part 161, From Token Streams to Structured ASTs. It was published on June 13th, 2026 by a developer named Ang.
And, while Haskell Programming Part 161 sounds like it signals we are going deep into the computer science weeds, and we are at the core architectural problem that Ang is dissecting here is something literally anyone managing complex systems encounters.
Right.
It's that everyday friction of moving from a messy, flat, generic data pool to a strictly typed, organized, hierarchical structure.
Yeah, I mean, even if you don't write a single line of code, this is about moving from a system where you just throw everything in a pile to a clean system where finding exactly what you need is completely effortless.
Exactly. It's about categorization.
So we're looking at this transition from chaos to clarity, but implemented at a really granular code level. And to truly appreciate the solution here, I think we have to start with the before state, the muddy waters, so to speak.
The token stream.
Right, the token stream trap. Ang describes their original approach for parsing text documents into their system, and they were using this token stream. Now, for anyone dealing with text processing, token streams are like incredibly common for that initial lexing phase.
Oh yeah, standard practice.
But Ang was using this flat token stream as the primary data structure for the entire conversion pipeline.
Right. And the output there was simply represented in the Haskell code as a list of tokens, an array. It's denoted as a token bracket. So you run the parser over a document. It identifies discrete elements like, oh, here's a YAML header, a title, a paragraph, a bold word.
Yeah.
And it instantiates a token for each one. But then, and this is the kicker, it just drops every single one of those tokens into a single one-dimensional list.
Okay, so to make this relatable, it's kind of like coming home from the grocery store, right?
Okay, I like this.
And instead of putting things in the fridge or the pantry, you just dump the receipt, the milk, the apples, all of it, into one giant, unorganized bin in the middle of the kitchen.
That is exactly what's happening in the memory. So the system possesses some semantic awareness of the individual pieces, like it knows a specific token is the milk or an author's name, and another token is a code block.
But it has no spatial awareness.
Exactly. There is absolutely no hierarchy. The metadata, the structural headers, the body text, they're all just sitting adjacent to each other in one long sequential array.
So the relationship between the components is completely lost. You just have this bucket of parts. And when Ang's program needed to convert that token stream into a final format, it really had to grapple with this flat architecture.
It did. And Ang explicitly notes in the post that this approach was, quote, rather tedious for the converter to extract details from the list.
Right. And wait, let's actually look at that performance hit for a second.
Sure.
Because Haskell is a functional language. It's heavily optimized for list processing. So why was a flat list causing such a noticeable performance nag? I mean, is it an issue with lazy evaluation or just the sheer volume of elements?
It's really the traversal complexity combined with the structural ambiguity. Think about how a flat list forces the CPU to behave.
Okay.
If you need to locate the metadata to extract the document's keywords, you can't just query a metadata field. It doesn't exist. The program has to initiate an O of N scan.
So it has to look at every single item.
Exactly. It looks at the first token, asks, is this metadata? No. It moves to the second. Is this metadata? It evaluates every single token in the sequence.
Oh, wow. So if you have a massive document, you are literally iterating through thousands of paragraph tokens just to confirm you've extracted all the book-level details.
Yes, you're constantly forcing the runtime environment to ask, what am I looking at right now? over and over and over again.
That sounds exhausting for the system.
It generates immense computational overhead. So the tediousness Ang mentions, it isn't just human frustration in writing the extraction functions. It is literal CPU cycle waste.
Right.
You're leaning on filter functions and pattern matching across this massive heterogeneous list when you really should just be performing a direct O of 1 memory lookup. Ang realized this flat processing was inherently fragile and slow. They basically hit a wall with the token stream.
Which brings us to the after state, the structural rethink. Ang completely abandons the flat list and introduces a structured document approach.
Yeah.
An AST, or abstract syntax tree.
Moving to an AST, it represents a massive philosophical shift in data modeling. You're finally separating the concern.
Okay, let's unpack this for a second. What exactly does this new structure look like in the code? How do we, categorize the groceries from our bin?
Right, so you stop treating a document as just a sequence of events and start treating it as a defined physical object with specific dedicated regions. You introduce a strict hierarchy. Ang defines 3 specific new Haskell data types to do this. The first one is metadata. This isolates all those book-level details that typically reside in a YAML header. The code strictly defines metadata as capturing the title as a text type, the author as a text type, and an index, which is an array of text strings for the keywords.
So by instantiating metadata as its own distinct type, the parser isn't generating generic tokens for the title anymore. It's creating a highly specialized object.
Precisely. And that object becomes a component of the second new type Ang introduces, which is the document type.
Right, the document type, which is our root node in the AST. It acts as the ultimate container. And what I find really elegant about Ang's implementation here is how the document type is completely compartmentalized. It contains a field called doc metadata, which holds our dedicated metadata object. But it's defined as an optional field.
Which is a brilliant defensive programming move. Using an optional type, like maybe in Haskell it means the system can ingest a document that completely lacks a YAML header and it won't throw a null pointer exception.
Or force the parser to inject dummy data just to fill a blank.
Right. The type system itself guarantees safety. If the metadata is there, it's strictly formatted. If it's not, the compiler knows exactly how to handle the absence natively.
That makes so much sense. And then, alongside that optional doc metadata field, the document type has a doc body field, and this is where the actual content lives, right? But it's not just a string of text. It's a list of the third new data type, block.
Yes, the block type is what replaces the absolute chaos of the old body tokens. It utilizes Haskell's sum types to enforce strict categorization. A block is explicitly defined as either a block header, which inherently encapsulates the header type, its level in the hierarchy and the text, or a block paragraph, which just holds the body text.
The structural guarantees here are phenomenal. You have a document node, you can query its doc metadata instantly, and you can traverse its doc body, knowing with absolute certainty that every single element inside is fundamentally a structural block, not a stray metadata token hiding in the weeds.
You've completely eliminated the ambiguity. You've basically traded runtime computation for compile time structure. The shape of the data now inherently reflects the reality of a text document.
But okay, this is where I have to play the skeptic a bit, or look critically at the implementation, because Ang includes the actual code diffs in the post. They show the lines deleted and the lines added to rewire the parser for this new AST. And the parsing logic itself, the combinator's actually reading the strings of text.
Yeah.
It didn't really change that much.
No, the mechanics of text consumption remained largely untouched.
Right. The diff shows pay metadata used to parse the YAML and return a generic token. Now it parses the same YAML and returns the metadata type. Header and new paragraph used to return a token, and now they return a block. And the overarching ptoken function was simply swapped out for a pblock function. So if the core parsing rules are essentially identical, and the only real difference is just the label applied to the return type, is it really worth the effort to refactor the entire system? Like, why go through the risk of a massive pull request just to change the wrapping paper on the same data?
Well, it is a very common developer trap to look at a parser and assume its primary job is text identification, but the true power of a parser isn't in how it reads. It's in the exact shape of the payload it hands over to the rest of the program.
Okay, right.
To see why this refactor was so critical, you have to look at the pdocument function in Ang's diff.
The assembly function.
Yes. Under the old token stream architecture, pdocument would parse the metadata, parse the body tokens, and then rely on Total list, maybe meta plus body.
Okay, let's pause on that because that plus plus operator in Haskell is notorious. It's the list concatenation operator. But wait, maybe meta is, at most, a single element list containing the parsed metadata. Concatenation of a single element to a larger list is an O of 1 operation.
It is.
So the plus plus itself isn't creating the massive performance drag during the parsing phase, is it?
You are spot on. The parser itself is executing that concatenation incredibly quickly. The catastrophic performance hit is the downstream consequence of that concatenation. By using plus plus, the parser actively destroys the boundary between the metadata and the body. It forces them into a unified, opaque list. The parser washes its hands and says, here's your data. But the downstream converter now has absolutely no idea where the metadata lives.
Oh, I see. It inherits the O of N scan penalty because the parser destroyed the structural context right at the finish line.
Exactly. It's architectural sabotage. The parser had the metadata isolated and then deliberately mixed it back into the general population before handing it off. But looking at the new AST system, pdocument abandons that plus plus operator entirely.
It transitions from concatenating lists to instantiating a record. The new code is simply return $document maybe meta body.
It hands over the fully assembled container. It preserves the isolation.
The groceries are put away.
Yes. The metadata goes into the metadata slot. The blocks go into the body slot. The output is fundamentally pre-organized. And the profound downstream effect of this pre-organization becomes really obvious when we move to the translation phase.
Right. The point where the Haskell codebase actually converts this ingested document into a final export format, like a PDF.
This is the payoff.
It really is. This is the moment where building a robust, strict system turns an agonizing workflow into an almost effortless pipeline. Ang details the replacement of the core conversion function. The old heavy function was tokens to Pandoc. It took the target export format, that massive opaque list of tokens, and the publication year, and attempted to spit out a formatted document.
And inside that tokens to Pandoc function is exactly where the CPU cycles were going to die, just scanning and filtering that flat list to isolate the metadata required by the Pandoc engine.
But the new function is beautifully minimal. It's just doc to Pandoc. It takes the target export format, our cleanly structured document AST, and the year. Ang highlights a critical realization here. The processing of the metadata is now entirely decoupled from the transformation of the body content.
Because you don't filter lists anymore. You pull the metadata directly from the doc metadata field via an O of 1 lookup.
Right.
The decoupling is what allows Ang to leverage one of Haskell's most powerful abstractions, the monoid instance. Because Pandoc, which is the universal document conversion engine, Ang relies on it, treats its internal document representations as monoids.
Okay, let's actually define the monoid in this context, because it sounds like, abstract category theory, but its practical application here is incredibly grounded.
Yeah. At its core, a monoid in Haskell is a type class for data structures that just know how to combine with themselves seamlessly.
Yeah.
A mono requires two things: an empty element, like an empty string or an empty list, and an associative binary operation to merge two elements together. So if you have two strings, hello and world, string concatenation is a monoidal operation. The strings merge into a single unified string type.
It's like pouring water into water. You don't end up with a list of two waters. You just have a larger pool of the exact same substance.
Perfectly stated. Pandoc's core document format is a monoid. By cleanly separating the metadata from the blocks in the custom AST, Ang's doc2Pandoc function can cleanly map the custom metadata into Pandoc's native metadata format, then map the custom blocks into Pandoc's native block format, and then just apply the Haskell monoid operator, which is represented by the less than greater than diamond symbol, to instantly fuse them together.
So there is no list manipulation. There is no forcing incompatible types into a generic array. You translate both discrete AST components into the universal Pandoc type, and the monoid operator merges them perfectly.
It is mathematical elegance applied to data processing. And the strict typing of the block sum type makes the actual formatting incredibly precise.
Yeah, the code diffs show a perfect example of this precision regarding PDF generation. Ang's system supports exporting to PDF, or a format called TIPST, which is a modern, highly efficient alternative to LaTeX for typesetting.
Which is great.
When the converter iterates over the doc body, it utilizes pattern matching to examine each block.
And because of the AST, the pattern matching is absolute.
Exactly. When the pattern matcher hits a blot header, it doesn't have to calculate probabilities. It knows 100% it is looking at a structural header. So if the requested export format is PDF or TIPST, Ang wrote a rule that injects a literal piece of raw code directly into the output. #pagebreak.
Which is wild because injecting a raw page break command is a highly destructive operation if you get it wrong.
Oh, totally. If you accidentally inject that into the middle of a paragraph because your token stream misidentified a bolded word as a header, you ruin the entire document layout.
But the AST guarantees safety. The type system promises that a block header is a true structural boundary. So injecting #pagebreak right before it processes the header text is totally safe. The structure allows for aggressive, highly specific formatting rules without the risk of collateral damage.
You build a strict architectural framework, and suddenly, rendering a complex, beautifully typeset tips document requires a fraction of the compute time and zero hacky workarounds. You query exactly what you need from the exact memory location it occupies. The performance issues just evaporate.
It's a massive triumph for the codebase. You read through the post and you expect Ang to declare victory right there. Like the token stream is eradicated, the document AST is strictly typed, the Pandoc conversion is leveraging elegant monoidal merges, the system is finally sound.
But, the defining trait of a great engineer is an inability to leave well enough alone.
Very true. A good engineer solves the bottleneck. A great engineer questions why the tunnel exists in the first place.
In the closing thoughts of the blog post, Ang drops a massive pivot. They write that while the refactoring from tokens to the AST was necessary, the architecture can still be significantly improved.
Yeah.
Ang proposes migrating away from the custom AST entirely.
They want to replace it with a custom Pandoc reader.
Okay, we need to analyze this plot twist. Ang just spent this entire cycle architecting the perfect internal system. The metadata record, the document container, the block sum types. Why plan to rip it all out?
Because Ang recognized that their beautiful, perfectly typed AST is still fundamentally an intermediate representation. It's a middleman.
A perfectly efficient middleman, but a middleman nonetheless.
Exactly. Look at the flow of data. The raw text is parsed into Ang's custom Haskell AST, and then almost immediately the doc2pandoc function maps that custom AST into Pandoc's native AST format to utilize the monoidal merge.
You are translating the text from English to French, just so you can immediately translate it from French to Spanish.
Yes. The custom AST adds an entire layer of memory allocation and structural mapping that is ultimately redundant, because Pandoc already possesses a world-class, heavily optimized internal AST.
So by building a custom Pandoc reader, Ang is proposing to bypass the intermediate representation entirely. The Haskell parser would consume the raw text strings and instantiate them directly into Pandoc's native internal data structures.
Hooking the parser straight into the engine. You eliminate the need to maintain your own metadata or block types. You basically delegate all the architectural heavy lifting to a universal standard that is maintained by the open source community, rather than maintaining a bespoke structural model in your own codebase.
It is the ultimate software optimization, deleting code. Removing a perfectly functional internal system because a mature, standardized engine can ingest your data natively.
It highlights a really vital phase in software evolution. The token stream was chaotic, so they built custom order. But custom order carries maintenance overhead. The final evolution is standardized integration.
It's a brilliant arc. Ang moved from a generic flat array that forced the CPU to constantly search for context to a deeply custom abstract syntax tree that rigidly defined every piece of the document layout, making the translation phase elegant and safe.
But the AST was a mandatory stepping stone. You can't map raw text directly into a complex engine like Pandoc until you truly understand the structural boundaries of your own data. The custom AST forced Ang to map the territory.
Right. And once the territory was mapped, they realized they didn't need to own the cartography tools. The journey from the token stream to the Pandoc reader leaves us with a pretty compelling architectural philosophy to consider.
It really challenges the instinct to build proprietary solutions for universal problems.
Exactly. I mean, think about it. Whether you are architecting a microservice, structuring a database, or even, honestly, designing the operational workflow of a business, at what point does constructing your own perfect, bespoke internal framework become a liability? When is it less efficient to maintain your beautiful custom AST? And more efficient to just adapt your raw inputs to plug directly into the massive standardized engines that already dominate the ecosystem. We often celebrate the bespoke systems we build, but true efficiency might just be having the wisdom to realize your custom architecture is a middleman.
The goal isn't to build the best intermediate representation. The goal is the final output. Anything that delays that output is friction, no matter how elegantly it's typed.
A profound reminder to evaluate the middlemen in our own pipelines. Thank you for joining us on this deep dive.